Folks, welcome to the next lecture of electromagnetism. When I first learned about the rectangular Laplacian, I was so confused. But step by step, I solved every single one of my misconceptions. And today, I'm going to explain to you the rectangular Laplacian the way that I wished I had first learned it. I'm going to walk you step by step examples of the rectangular Laplacian. Let's get into it.
You said it's a slow ride, everything's gonna be alright. All I gotta do is just hold tight, everything is gonna be fine.
Here's another view of problem 1. Alright folks, let's start with a quick review of our previous lecture, and then I'm going to show you step by step, no step skipped, how to solve for the electric potential using the rectangular Laplacian. Let's start with a brief review. So, we learned previously that the end goal for electrostatics is to determine the electric field for an arbitrary charge distribution, right? And now we have an arsenal. We have a toolkit with many different tools to help us find the electric field. The oldest tool in our toolkit is this, Coulomb's law. Coulomb's law tells us the following. Coulomb's law tells us that the electric field is an inverse square field, just like gravity, which is equal to 1 over 4 pi epsilon naught q over r squared r vector for an arbitrary point charge. Now, this is Coulomb's law, but there's much better ways of determining the electric fields. For example, if you have a symmetric electric field, then what can you do? Well, you can use Gauss's law. Gauss's law. And Gauss's law helps us find the electric fields for continuous distributions. So for example, if you have an infinite planar sheet or a cylindrical coaxial cylinders, or if you have a sphere, then Gauss's law can be applied. And it helps you easily find the electric fields in situations where you otherwise couldn't find it using Coulomb's law. Now, Coulomb's law has a bit of a hitchhike. I should have put in the unit vector here, not the normal r vector. Otherwise, if I put the normal r vector, there should be a cube on the denominator. So that's Coulomb's and Gauss's law. But we can do better than that. In fact, we can find the electric potential first and then differentiate it and then negate it to find the electric field. And so we figured out how to solve Poisson's equation, nabla squared v is equal to minus rho over epsilon naught. After we solved that, we got the potential for an arbitrary charge distribution is just rho of r prime dr prime cubed over r. And of course, you're going to have your 1 over 4 pi epsilon naught SI units, right? So then after you differentiate that, you can get the electric fields, right? So the only reason you can do that though is because the curl of the electric fields is 0. So anyway, so we came up with a bunch of ways to figure out the electric field. TLDR, long story short. We found other ways. We could use image charges for very special charge distributions, like when you have a charge near a flat conducting plane. We figured out that you could use magnetic monopoles, right? So not magnetic monopoles. You can use monopole expansions for the electric field to figure out the field near an arbitrary charge distribution. But that's not what I'm here to talk about today. What I'm here to talk about today is the tactic we learned in the previous lecture, which is the Laplacian. The Laplacian applies when your volume charge density is 0. Okay, that doesn't necessarily mean you don't have any charge distribution. It could just be like you want to determine the potential in a region where you have no charge. In such a case, nabla squared v becomes 0, and suddenly you're trying to solve the Laplacian equation for the electric potential. And how do we do that? Well, here's what we learned in the previous video. What we did was we made a very brave assumption, but it turned out that it works just fine. We assumed that V, the electric potential, is separable, that you can break it up. chop it, slice it and dice it into a function of x and a function of y. After plugging that into there, we figured out that x of x and y of y can either be an exponential function or a sine function. Exponential function or a sine function. And you can also have z of z if you're in 3 dimensions, which we'll see today. But anyway, I'm keeping it simple in this case. So we have to decide, is x going to be exponential or sine? Is y going to be exponential or sine? And we had to decide that based on our boundary conditions, right? So you always have to write down your boundary conditions for these problems. And based on that, you can decide what kind of function x and y are going to take on. Okay, great. So now that you've figured out what kind of functions x and y are going to be, you can write out your whole potential function as c sub n, x of x, and y of y. And your final step, step 5, would be to determine this expansion coefficient. So determine c sub m using the trick we learned in our previous lecture, Fourier's trick. Right? So these are the 5 easy steps, but they're not easy. They sound easy, but you have to practice a lot of times for these really to be at the back of your hand. So let's get started with our first practice problem. Alright, so here's our first problem. An infinite slot between x is 0 and a, so x starts from 0 and ends at a, right here. Between y is 0 and infinity, and between z is negative infinity to infinity, meaning that we're symmetrical around z, meaning we don't have to consider z for this problem, is oriented as shown. So here we've got our 2 plates, if you will. We've got a potential at this bottom plate between x is 0 and a of this much, and these 2 plates are grounded, right? So their electric potential is 0 over here and over here. So the sides at x equals 0 and x equals a are grounded, while the end at y equals 0 is charged so that the electric potential is this much, where k is a constant. If there's no charge in the slot, so there's no charges here, hence Laplace's equation applies, find the potential in the slot. Okay, so let's start from the basics. What is our fundamental equation for the Laplacian? The fundamental equation is this. We start from Poisson's equation, which tells us that nabla squared of the electric potential is minus the volume charge density over epsilon naught. Where does this come from? This simply comes from Maxwell's equation that the divergence of the electric field is the charge density, volume charge density over epsilon naught. But we know that the electric field is nothing more than minus the electric potential, gradient of the electric potential. And that's where you get this from. And that's where this minus sign comes from, by the way. So that's where this whole equation comes from. So in this case, we don't have any charge in the slot. Hence, Poisson's equation becomes Laplace's equation. Okay? And then we say that, okay, let's be brave. Let's say, what if our best wishes came true and the electric potential was not some wacky function, but instead it was a separable function such that you could separate out the x as a function of just lowercase x and the y as just a function of lowercase y, right? So that's the assumption we made. And after we made that and plugged this back into here, what did we get? We got this equation. X double prime over x plus y double prime over y equals 0. After we plugged this into this, that's what we got. Just rewind back to yesterday's video and you'll see how we got this. And so after we got this, there's only one conclusion to be had. And that is that these 2 guys are constants, right? And so if they're constants, that means that x double prime is some constant times x, and y double prime is minus that same constant times y. But that means x and y are either exponentials or sinusoidals. So try to follow this chain of logic. All this is a beautiful chain of logic. And please try your best to follow it, or you can ask any questions you have down in the comments below. After this, we figured out, okay, you know what? It doesn't have to be this way. It could be that all they have to do is add up to 0, right? So I could have made this constant negative. Or in either way, either this constant or this constant has to be negative. I have to choose which one is negative based on my physical situation. Okay, so let's see. So x is either exponential or sinusoidal, and y is either exponential or sinusoidal. Let's see. Okay, so here, what are my boundary conditions? So to answer this question, I have to come up with my boundary conditions. So let me write down my boundary conditions. So for this problem, my boundary conditions, why don't we write that down? Boundary conditions are that at these two plates, we have 0 electric potential because they're grounded, right? In other words, mathematically, the potential at x equals 0 and y equals whatever is 0, and the potential at x equals a and y equals whatever is also 0. We have more. We know that the potential at this bottom lower plate, when y is 0 but x can be anything, is fixed at k sine 2 pi x over a. And finally, the potential all the way up. As you go up, there's no more charge in this plate, right? So the potential is going to go down, all the way to 0. As y approaches infinity, the electric potential, approaches 0. So these are our 4 boundary conditions, okay? So I'm going to actually label these 4 boundary conditions. Okay, so here are our 4 boundary conditions. Now let's use them to figure out, should x be exponential or sinusoidal? Should y be exponential or sinusoidal? Well, when x is 0, potential is 0. Gotcha. When x is a, potential is 0 again. Wait, what kind of function starts at a value and comes back to the same value? Is it an exponential or a sinusoidal? Well, I'm pretty sure that the only way you can start at 0 and come back to 0 is if you have some kind of a sinusoidal. Definitely, if you have an exponential, it's never going to come back to what it used to be. Therefore, x must be a sinusoidal. It must be an oscillating function. So x must be oscillating. What about y? Let's see. For y, we start at, when y is 0, we have a fixed potential of k sine 2 pi x over a. So the potential varies across x, but when y is 0, this is the potential. But as you go up, as you increase in y, as you go up this slot, the potential starts decreasing because there's no more charge in this slot. Potential starts heading to 0. So, should the potential in the y direction be represented by an exponential or a sinusoidal? Well, does the potential in the y direction ever come back to its original value? No, it just keeps on heading straight down to 0. In fact, it seems to just be decreasing. It's a one-way function, one-way highway. So it must be an exponential, not a sinusoidal, because it does not return to its original value, right? So y is the non-oscillating function. Okay, so we figured out what x has to be, what kind of function y has to be. Now we can write out a general function for x and y as a linear combination of sinusoidals and exponentials. So let's do that. So I'm going to now say, hopefully you can still see here, or I can write over here. We can now say that x is a sinusoidal. So, okay, so what did I just write? Okay, well, I know a sinusoidal function is some kind of a function that is made up of sines, right? So if I want to make any function out of sines, here's what I would do. I would take a mixture of sines and cosines, right? All you're seeing right here is a mixture, or in math, what we call a linear combination. You see, when you're cooking a recipe, if you want to get creative, you're going to get more ingredients. The more ingredients you can get, the more things you can make with your cooking. In the same way, we've got not only sine but cosine here mixed in, so that we can make any function we want just from these two. In linear algebra, this is known as a basis set, right? Sine and cosine are a fundamental basis that we can use to create any function that we want. So, and these a and b just controls how much of each ingredient we want. Say I want just a sinusoidal function, no cosines. Well, then I turn a all the way up and kill b and make it 0. Okay, so that's the idea. And what about for the function y? Well, y is an exponential. What is the basis set for an exponential? Well, it's a growing exponential, e to the kx, and a decaying exponential, e to the minus kx. And as usual, I'm going to put down some constants here so I can control how much of decaying and how much of growing I'd like. Now, we're going to impose our boundary conditions so that we can figure out what these constants a, b, c, d are. Let's impose them. Okay, let's take a look at our first boundary condition. It tells us that when x is 0, the potential has got to be 0. Okay, let's look at x. When x is 0, the potential has to be 0. Let's plug that in. Let's plug in x is 0. So I'm going to bring this over here. So when x is 0, that's equal to a sine kx, a sine k, well, k times 0, that's going to be 0, plus b cosine kx, well, k times 0, again 0, so cosine of 0. Well, sine of 0, that's just 0, that's okay. So this thing is gone. Sine of 0 is just 0. Cosine of 0 is 1, so I can just erase it. And so we're left with b. X of 0 is b. But what does the potential have to be when x is 0? That's right, it has to be 0, right? So that means b, our constant b, is 0. Oh, what do you know? That means this whole term is gone. It's 0, for Christ's sake, right? So we can take it out. It's gone. So let me just write that this is 0 by our first boundary condition, by 1, boundary condition 1. Okay, let's see if we can kill off any other constants using the same idea, by imposing our boundary conditions. The second boundary condition tells us that the electric potential when x is a is 0. Okay, well, let's see, what does that help us with? Well, when x is a, let's do the same thing. Let's plug it in. So when x is a, what are we going to have? Remember, this term is gone now. I crossed it out. It's 0 because of this constant b we figured out was 0. So the whole term was gone because of the first boundary condition, right? So because when x is 0, the potential had to be 0, and cosine is not 0. For x is 0, cosine is 1 when x is 0. Thus, b had to be 0. So bottom line, this term is gone. So x of a is a sine k times a. A sine k times a. And we know this has to be, the potential has to be 0 there, right? So the potential has to be 0. Okay, well, how does that help us? Well, take a look. Let me divide both sides by a. So I'm left with sine of ka is 0. But when is sine 0? Sine is 0 when its argument is a multiple of pi. That means we just figured out what k is. K is n pi over a. That's what k is. So now I can just plug that value of k in here and here, and I can help solve for k. So we've just figured out what k is. We deleted one term, and so I have used boundary conditions 1 and 2. Success so far. So let me go ahead and erase some of the stuff we have. Okay, so let's write down what we have so far. We've just figured out that our x potential function is a sine kx, where k is n pi over a. So a sine kx, but k is n pi over a. So kx. And what about our y potential function? Well, y is this, but I'm going to simplify it just a bit more. I know that as y increases, the potential has got to decrease. Since there's no charge in the slot, as I go up the slot, potential's got to go down. But when x goes up, this is definitely going to go down, this term, because there's a minus sign. This is a decaying exponential, but this term is going to go up. It's going to try to compete. I don't want any competitors. Screw this guy. He's got to go. Because if he doesn't go, my y potential is going to jack up. I don't need that. So this c term has to be 0 because of the fourth boundary condition. Okay, so that means we're left with, for the y potential, we simply have d e to the minus kx, where k is n pi over a. Sorry, this should be a y here. I don't know why I mixed that up. This should also be a y here, since we're dealing with the y potential. So we have e to the minus n pi y over a. Okay, great. So now we are in business. So what do we have for our potential function? Now we can write our potential function v as a linear combination, c sub n, of these two guys, of the sinusoidal and the exponential. Okay, as n goes from 1 to infinity. In fact, why don't I write it out in full over here? The electric potential function is going to be, in general, the potential function is going to be from n equals 1 to infinity, your expansion coefficient c sub n, which you have to figure out, times x of x times y of y. Now we know what x of x and y of y are, so we can just plug them in. So we're going to have c sub n, x of x being sine of n pi x over a, and y sub y being e to the minus n pi y over a, as n starts from 1 to infinity. It's important that you know the limits of your summation. So now we can go ahead and figure out what our expansion coefficient has to be by imposing our third boundary condition. We exhausted all the four boundary conditions, the first, the second, the fourth, but not, as you will notice, the third. So let's exhaust it. So the third boundary condition tells me that when y is 0, I will have the following potential. So when y is 0, my potential will be k sine 2 pi x over a. And this will be equal to all of this when y is 0. And x is, well, x. N is going from 1 to infinity. C sub n, which I'm trying to figure out the expansion coefficient, sine of n pi x over a. And now, because y is 0, look, when y is 0, this whole thing is 0, and e to the 0 is 1. So I don't need to write that term, right? So this is what I'm left with. And now, we don't even have to use Fourier's trick. We could, if we wanted. You could very well write out, if you really wanted to, you could really write out the integral from 0 to a of sine n prime pi x over a dx, and you could really do that if you wanted to. But just observe what we have here, right? Observe that we have 2 pi x over a n pi x over a sine k c sub n. What does that mean? That means we have a conspiracy theory on our hands, folks. No, it means that n equals 2 for our Laplacian. Only an equals 2 term survive, meaning that C sub 2 is equal to K. That's our expansion coefficient. And so what are we left with? We are left with, for our final potential function, which I will write in black, our final potential function, V of x, maybe this is not the best place to write it, V of x comma y is equal to this K sine 2 pi x over a, K sine 2 pi x over a times my decaying exponential, and now I know that n is 2. So e to the minus 2 pi y over a. Alright folks, that right there is my potential. And now let's do a quick review of what just happened. It can be a lot to handle, but let's go through it step by step. We figured out that our x potential function has to be a sinusoidal and our y has to be a decaying exponential by applying these 4 boundary conditions. And then we wrote out our potential function v as a linear combination of our x and our y functions. Notice that here is our x potential function and here is our y potential function. Notice how all we had to do was multiply them together because of our assumption at the very beginning that they were separable, that the potential function was separable. And so then we've applied the last boundary condition, the third boundary condition, to figure out the expansion coefficient. And if you wanted, you could use Fourier's trick, but in this case you didn't have to. And so this was our final answer. This was the electric potential in this case. So folks, hopefully you found this example helpful, and we'll see you in the next one.